Hi all. So in this video, we're going to talk about orthogonal linear operators. We've been doing a lot of heavy lifting throughout the rest of the lectures this week. Kind of talk about what a linear operator is, what the matrices are, what eigenvalues, eigenvectors, etc. So there's been a lot of heavy lifting. And so now we're going to ask about what happens when we talk about a particular thing called orthogonal linear operator. So what's an orthogonal linear operator? This should be a kind of lighter lecture. It'll be more heavy thinking because we're going to do a proof of a proposition. But other than that, it shouldn't be too bad. So we're going to say an orthogonal linear operator P if it preserves the inner product. So basically, we have P preserves the inner product. So what does preserves inner product mean? Preserves inner product means that if I take P on some vector X, and I take P on some vector Y, the inner product should not depend on this operator. So in other words, whether I've done the linear operator on X and Y or not, this should stay the same. And that is the case. This should be the case for every X and every Y in our vector space. So this should be true for everything. Nice and easy. And so we're going to look at, okay, how does this relate to kind of everything we've done so far? So we're going to look at this proposition, which basically relates all the things we've seen so far to kind of one another. So B is going to be some orthonormal basis. P is our linear operator. Now, the following are equivalent. So P is an orthogonal operator. So this is basically what we just defined. Operator. This is going to be equivalent to P of B being an orthonormal basis. So remember, orthonormal basis was when the inner product gives Kronecker delta, right? The third condition is that P of B, so the linear operator, the matrix of the linear operator with regards to the basis B, if this is an orthogonal matrix, right? So orthogonal matrix, this was when we had MTM is equal to the identity. So the first two conditions we've already seen. This is proposition 1.32. So this is not too bad. What we're now going to show is P being orthogonal and P of B being orthonormal are the same. So that is basically what we're going to do. So what we want to show P orthogonal if and only if we have P of B orthonormal. So in other words, if P of X, P of Y gives XY, if and only if EI EJ is equal to the Kronecker delta IJ. Okay. One direction is easy. So if I start off with so this is direction 1. This is the forward direction. If I start off with some orthogonal operator, then my equation 1.18, right? This is precisely the definition. If we do it on the basis elements, right? So if I take this, right? And I look at this inner product, these are the same, right? And so this gives me this equality, right? Why is this true? This right-hand side, right? Why is this part true? This is since B is orthonormal, right? So in our proposition, we assume that B is an orthonormal basis. I should choose a different color. This is important. B has to be an orthonormal basis. So if it's not orthonormal, we already failed the first part. So this has to be orthonormal. Now what this is saying is that this right-hand side gives us the Kronecker delta, and that implies that P of B is orthonormal. So that gives us halfway done. So we have one direction and we're done. So in the other direction, we're going to start off with P of B being an orthonormal basis, okay? And we're going to look at two arbitrary vectors. So we're going to look at x here, right? So x is some vector, y is some vector. And these are going to be living in V, right? So let's look at these things. Here we have the inner product, right? This is just the normal definition of the inner product. And I'm going to plug in the values of x. So this is just x, and this is just y. Now, linearity of P allows me to pull out all of these x's and all the y's. And so we end up having this summation. Now, the linearity of linearity in this case gives us that we can pull out we can pull these out. Pull out the xi, yj. So we end up with this formula. Here, I guess I should have been a little more precise, this notation. So by this, I really mean same as before, ij equal to 1 to n. It's just super shorthand. Sorry about that. Now, since P of B is orthonormal, what we know is that when I look at the basis elements, this is just the canonical delta, ij. So what this means is I can smush this equation together and just get that P of x, P of y gives me this. So in other words, this gives me the dot product. Therefore, inner product is canonical. Is a canonical dot product. But what we have is, if we recall 1.9, so let's look at 1.9 here. I think I can do it this way. So if I look at equation 1.9, right, this is this whole fun thing. We basically said that in this case, this equation here, which is exactly what we have, right, x of y is equal to the inner product, then this gives us an orthonormal basis. So this is on page 2. If that helps, or I guess technically page 13 if we're looking at all the notes. And that when x and y are written in an orthonormal basis, their inner product is precisely this. So this is kind of what we had discussed at the very beginning. Now this agrees for P of xy, which means that P itself is orthogonal. And that's basically it. So here we have that P is orthogonal, and that gives us the second half, and we're done. Now, what this means is, as a corollary of the proposition, remember there was a remark that we said that the determinant is always plus or minus 1 for the orthonormal matrix, right? For the orthogonal matrix, the determinant is plus or minus 1. What this means is if P is an orthogonal operator, then its determinant is plus or minus 1. Determinant of an orthogonal operator is always plus or minus 1. In other words, they're always invertible. So that's another nice thing about orthogonal linear operators. They're always invertible. So this is like sometimes a nice, easy way to check whether you have something orthogonal. You just look, if the determinant is not plus or minus 1, you know that it's not orthogonal. But if it is plus or minus 1, you're still going to have to double check whether it is orthogonal or not. But at least it gives you a little hint that maybe it might be. So anyway, we'll end it here for today. As you can see, this is the last page. So we will end this week here. And I will see you all next week for week 3. Have fun. Peace.